So this is the first and perhaps the simplest app in this project in Grasta, which helps you to understand how actually non-parametric statistics allows you to summarize data, to describe your data, and also how to visualize it using some simple plots like box and whiskers plots. So let's start with the table. So what we have here, it's our sample. It consists of 12 values. And in this case, I took IQ of people just randomly taken from the population. So we have 12 random people, and then we have corresponding IQ values here. The idea of non-parametric statistics is following. First of all, we order these values. You can see this is the smallest value, this is the largest value, and then every value has a rank, 1, 2, 3, 4, 5, up to 12. Now we can think, okay, 12 values span 100%. So how much we have in between the first two? Apparently it will be 1 divided to 12, right? So it means that it's approximately 8.33% of the values. Then you have also 8.33% here, 8.33% here, and so on and so forth. Now we can ask ourselves, so how many values we have smaller than this one? Apparently it's 0, so we can write 0% of values here. Now how many values we have smaller than this one? Apparently it's 1, only one value smaller than this one in our sample. And therefore we can say that it's 1 over 12 values in percent, right? Or it's exactly this 8.33%. Then how many values smaller than this one? Now we have 2, right? So it means that it's 2 over 12 or 16.6666 and so on percent. And then we can just continue, and then the last value have 11 smaller than this one. And it means that the percentage will be 11 over 12 or 91.66666%. Okay. So these values are called sample quantiles. And this is one of the ways to compute the sample quantiles. And this way has one big drawback. You can see that all this percentage, they sort of shifted towards 0, right? So you have some gap here. So this can be overcome in many different ways, and there are many different ways to compute quantiles. In this particular app, I use the following. I move these values, the real values, not as boundaries of these intervals, but as middle points. So instead of having 0% here, I say, okay, it's somewhere between 0 and 8.33%. So it means that it's 4.2%. If we round it, of course, it's 4.16, but if you round it, it will be 4.2%, right? So it means that I expect that approximately 4% of the values in my population will be smaller than this one. And apparently, if I have a bigger sample, for example, if I have a sample of 100 values, then this value will be much smaller, so it will go towards 0, right? For example, for 100 values, it will be 0.005, right? So it's like 0.5%. And then similar here, so in this case, you can see that I got a percent value, it's 95.8%, so it means that I expect that approximately 95.8% of the values will be smaller than this one in my population. And then, for example, if I have 100, then it will be 99.5, okay. So these values are called sample quantiles. Now we can use sample quantiles to compute different statistics. For example, so in this case, I split my interval of values to 12. But what if I split them to 4, for example? So I have 25% in each interval. So in this case, we need to do it in a sequence. First of all, we split it to half and a half. So apparently, it will be between the value number 6 and 7, right? And then look, if you look at this percent of value for 6 and percent of value for 7, what you have in between, it will be exactly 50%, right? And then it means that if you take a value equally distanced between these two, you will have 50% of the values smaller than this one, and 50% of the values larger than this one. So you will have the 50th percentile of your data set. And that's what we call also a median, or the second quartile. You can see it here in this table, so it's 110.8. Okay. Now you can continue and take only the smallest value. So you have 6 smallest values, and then you have 6 largest values, right? Take the 6 smallest values and find a median for these 6 smallest values. Apparently, the median for the 6 smallest values is between value 3 and 4. So you have 3 values smaller and 3 values larger, right? If you look at the quantile value for the value 3 and the value 4, you can see that what you have in between, it's exactly 25%, right? So it means that if you take a value between these two, it will be your median for 50% of smallest values, or we call it first quartile, because strictly speaking, it's a border between 25% of the smallest values and 75% of the largest values. This is Q1, and this is what we have it in the table. It's 105.8. Similarly, we can compute a third quartile. It's a median for the 50% of the largest values. Again, you can see that it's located here. So if you take a value between these two in the middle, you will get exactly 75%. And it means that if you take the IQ value between these two in the middle, that will be a third quartile, right? So it will be like a border between 25% of the largest values and 75% of the smallest values. And that's what you see here. Okay. Finally, of course, the first value in the sequence and the last value in the sequence are correspondingly the mean and the max, or the largest or the smallest values. Okay. Now you can visualize these statistics using this very simple plot, which is called the box and whiskers plot, and this is what you see here. So the box, this one, is formed by three quartiles. So you can see Q1 is here, Q2 is here, and Q3 is here. You can also see the real values, the points. You can see this is the axis, and these are the points corresponding to the values from the table. And then you can see, indeed, the Q1 is splitting your values to 3 on the left and 9 on the right. So exactly 25% on the left, right? Q2 splits your values to 6 and 6, so 50-50. And Q3 also splits your values to 9 smallest and 3 largest values, right? So this is the idea of the box. So box shows you this range for 50% of most common values. Why we call them most common? Because they do not exclude 25% smallest and 25% largest. They are always in the middle, right? So this is the box. And the whiskers, they show just the smallest value and the largest value. Okay. Sometimes you may have what is called outlier. Outlier is a value which is extremely large or extremely small in relating to the other values. And you can actually change it manually. You can see I can change the max and the mean. So let me change the max. So you can see it's going pretty far away from the rest. And at some point it becomes too extreme. So it becomes like an outlier, right? And the same like this one, right? However, when to consider it as an outlier and when not? Well, in box plot, there is a mechanism. There is like a kind of a method for detection of these kind of extreme values. And that's, you can see as red lines here. So these are detectors for outliers. And detectors are made as follows. First of all, look, when I change the mean, you can see that the box doesn't change. When I change the max, the box doesn't change. Because box is made using quartiles, and quartiles are based only on the ranks. They are not based on the values, right? They are based on the ranks, the position of the quartiles, and therefore they are stable to outliers. So therefore we will use box as an outlier detector. And the idea is following. We take this size of the box, the length of the box, it's called interquartile range. It's simply a difference between Q3 and Q1. Then we stretch it 50%, maybe we make it 50% longer. So we multiply the size of the box to 1.5. And then this is the red line. So the red line here, it's exactly the size of the box multiplied to 1.5. The red line here, it's exactly the size of the box multiplied to 1.5. And then you can see that if the value is larger than Q3 plus this red line, it will be considered as outlier. If value is smaller than Q1 minus this line, it will be also considered as an outlier. Let me take a new sample, so it will be a little bit easier to show you the outliers. For example, this one, right? Now look, I start increasing the largest value, and now you see I am on the border, right? What happens if I go just beyond this border? Look, now the whisker is here, and this value is shown separately. So now, because this value is beyond these outlier boundaries, box plot shows it as a separate value, as an outlier, and the whisker shows the next largest value here. Okay, and then you can see the same. Let me get back, and then you can see the same for the mean. So it's extreme, but it's still acceptable. Now it's on the border here, and then if I go beyond the border, you can see now again it's shown separately because now box plot considers this as an outlier, and therefore the whisker is located at the position of the next smallest values. Okay, so that's how box plot works. And then you can see that every time I take a new sample, although this sample is taken from the same population, so it means that statistically all these samples should be similar. You can see a very different picture. Look how different the box plots are when you take a new sample from the same population. Also, it's a random sample, so it's very good sampling here. Okay, so my point is that box plot can be a little bit misleading because box plot, when you make it for a small sample size, and 12 is kind of small sample size for the box plot, right? Because you need to compute 5 statistics to make a box plot, and you have only 12 values. Take it with caution. So the box plot doesn't always shows you the real situation in your population, right? It's just an approximation of what's going on in your population. And then finally, you can see that I also have a mean, the average value, which is shown as a dashed line here. And you can see that in contrast, mean is sensitive to outlier. So every time you change max value or the mean value, you can see that mean position is also changing, while the median is always the same, right? So median is pretty stable to the outliers, okay? So go on and play with this app, and then you will probably understand this a little bit better.